now we have Peter Brown speaking about randomness expansion protocols.
So first of all, again, another well-deserved thank you goes to the organizers for this event. And I'd like to also personally thank Glaucia for making this talk a lot easier to present. So I'm going to talk about some joint work with Sami Raji and Roger Colbeck at the University of York in the UK, where we looked at constructing device-independent randomness expansion protocols with security based on numerical techniques. The archive number of the relevant paper is here, and all of the code implementing our framework can be found at this GitHub repository. So first of all, so we're all on the same page, let me quickly introduce the task of randomness expansion. So we're going to assume that we have access to some private random seed. And when we say private, what we mean is this is uncorrelated with any adversary system. And we want to find some way of taking this seed and generating a much larger amount of randomness. And we want to do so in such a way that this end output string is still private. So a few requirements: we want to increase the amount of randomness we have, otherwise this is kind of pointless. And we also want some assurance of privacy. So if we get an output here, we want something that tells us that this is definitely private. And because we're going to work in the device-independent setting, we want to do this in a way that's independent of the mechanism here that's generating this string. So quickly, just reviewing some entropy preliminaries. We heard that before that we have a few different entropies that we can use to characterize randomness. And the one in particular that we're going to use here is the min entropy. And it has this very nice operational interpretation where it characterizes the number of uniform bits that are contained within the output of our source. So if we imagine that x is a random variable and it outputs a big long bit string, then the min entropy of x tells us how much we have to compress this output in order to get uniformly random bits. And as well as this, the min entropy is kind of cryptographically a very natural quantity. It has this adversarial scenario built into its definition. So if x is a random variable, then the min entropy of x is going to be minus log of the probability that we can guess the outcome of x. And so this guessing probability form extends itself to when also we have extra correlations with this random variable and even quantum correlations. So now suppose we have this classical quantum state. So now we have our random variable x, which is just a mixture over some projections, some orthonormal basis. And this is now correlated with some other system E. So we can imagine this state came from, we had a bipartite system, and we measured on one part of that system. And now what we want to say is, okay, what's the probability that we can guess correctly given we have access to this second system? And again, this is going to be minus log of the probability we can guess correctly. So now we have a slightly more sophisticated method of guessing the outcome. So we can perform a measurement on this second system, and then corresponding to the outcome of that measurement, we're going to guess the outcome of the random variable x. And now maximizing over all possible measurements, we get the maximum probability of guessing correctly. Okay, so so quantum theory gives us a very natural platform for generating random numbers. So a very, very simple quantum random number generator could be something that looks a bit like this. So we send in some sigma x eigenstates, and we measure in the sigma z basis, and we know we get perfectly random bits from this setup. But the only problem here is that we only know that this final output string is random because we know the states and with the measurements that are going on here. So we can imagine a slight change in scenario where somebody may have tampered with our random number generator here. And all they've done is they've taken the outputs of a actual quantum random number generator, stored them on a hard drive, and stuck the hard drive inside of our box. And now whenever we ask for some random bits, the box is just going to output this bit string from the hard drive. Now from our perspective, this random bit string is perfect. It's perfectly random. We can't distinguish it from this device over here. But if we have knowledge of the hard drive and the contents, then this is an entirely deterministic process. So when we ask of whether this is still random, it really depends on the application. And if we're thinking about cryptography, we maybe want to trust as little as possible. And so kind of the extreme version of that, as we heard in Glaucia's talk, is device independence, where we try and remove as much trust about the situation as we can. And the reason that we can do this is because non-local correlations actually act as witnesses to private randomness. And so what do we mean by this? Well, if we take the standard Bell setup, where we have two devices, and we separate them so they can't signal to each other, and we feed them random inputs and we get outputs, then if we observe some non-local correlations here, then it has to be that the outputs of the devices were non-deterministic. And this is non-deterministic even if you know the inputs that went into the device and any arbitrary side information. So you can know the state that came in here and the measurements, and you still can't guess the outcomes with certainty. And so the idea then is then we can use these Bell violations or these non-local correlations as certificates for the random bits that are coming out of our devices. Okay, so wrapping this into a protocol now, first of all, we take our devices, we stick them in our secure laboratory, and we separate them so they can't signal to each other, feed inputs, get outputs, and we repeat this process many, many times until we get some big, large bit strings A and B. And then we're going to ask the question, did we observe any non-local correlations? And if we did, how much entropy does this certify about the outputs of our device? And finally, going back to the operational interpretation of the min entropy, we can then compress this randomness into perfectly uniform bits, depending on the quantity that we can certify. But this second part here, where we go from non-local correlations to entropy, is going to be the main focus of this work. Okay, so after the first step of our protocol, we're going to have something that looks a bit like this. We're going to have generated the randomness, but we're assuming that when we generated the randomness, maybe an adversary had some purification of the state that went into the device, and they're able to store this in some quantum memory. And we say, okay, if we observed over the course of this interaction phase some average non-local score, then how much entropy is contained within the outputs here? And so, as we heard before, we have a nice theoretical technique here that lets us take the total amount of entropy and calculate it in terms of the entropy of a single round. So the entropy accumulation theorem says that with high probability, the total amount of entropy here is going to be around n times the entropy of a single round, assuming that the devices obey this average non-local score. But in order to use this entropy accumulation theorem, we have to be able to construct these min trade-off functions. So these are the lower bounds on the single round randomness. And now a min trade-off function, what it is, it's a map from the non-local correlations to the reals, and it obeys two things. So first of all, it's affine, so it's just a scalar plus some linear term in the score, and it also has to be randomness bounding. So if we feed in a non-local score, it has to give us a lower bound on the von Neumann entropy of a single round. And this is a lower bound on the von Neumann entropy for any states and measurements that are expecting to score this C. Now, again, as we heard before, this is very difficult to compute in general, in a device-independent way, that is. And we only actually know of one scenario in which we can actually compute this in a tight way. But we can easily bound it. So we know that the von Neumann entropy is always greater than the min entropy. So if we can construct these min trade-off functions with respect to the min entropy, then we immediately have min trade-off functions for the von Neumann entropy. So luckily for us, the min entropy we can compute, and we compute this in a very general way. So again, the min entropy is minus log of this guessing probability, and the guessing probability is a convex optimization problem. So we can rewrite this in a device-independent way. So informally, what this is we say that the guessing probability is going to be the maximum that our adversary guesses correctly, subject to the devices obeyed this non-local score here, so they expect to score this C, and the devices are restricted by quantum theory. And so what this means is the correlations we observe have to come from states and measurements. Now, this set here is actually quite difficult to implement in practice. But what we can do is we can relax this. So we can look at outer approximations to this set. And these outer approximations then become a constraint, which is just positive semi-definiteness of some matrix. And the great thing about this is the convex optimization problem becomes a semi-definite program, and semi-definite programs we can solve in a computationally efficient way. And because these are outer approximations, this is going to be an upper bound on the guessing probability, and that's going to be a lower bound on the min entropy. So we recover the randomness bounding property. Now, if we just look at the primal, we can compute for a particular point a bound on the min entropy. But what we want is a min trade-off function. So you want some function that gives us a bound for all possible non-local scores. So we can take the primal and then go to the dual program. And what the dual program looks for is it looks for some function that is affine and is everywhere an upper bound on the guessing probability. So if we imagine that we, in the primal setting, if we imagine that we plot kind of the curve that's associated with this guessing probability, the non-local score, then we get some concave curve that looks a bit like this. And what the dual program is looking for is it's looking for the tangent lines of this curve. And in general, we can have multiple non-local scores, and we get tangent planes, tangent hyperplanes, and so on. Now, this dual program here, it's really giving us this function now. So it's saying that we're going to get a function that everywhere upper bounds the guessing probability. So if we take minus log of this function, we're going to get something that is everywhere a lower bound on the min entropy. And so we just take a first order approximation of this, and we recover the affine property. And now for every single tangent line here, we have a min trade-off function. So now we have a full family of min trade-off functions that we can use. And now we're able to use the entropy accumulation theorem to get a bound on the total amount of randomness that we have. So what we've shown is that we can use the entropy accumulation theorem because we can construct these min trade-off functions from the outputs of our semi-definite programs. And so if you fiddle about with this for a while, you can show that you can write all of your security statements in terms of the outputs of these STPs. And so what that means is now a user can come along and design their own protocol. So they can choose their non-locality tests and their security parameters, and they can compute the semi-definite program, and that gives them a way to calculate the accumulation rates of the protocol and evaluate the quality of the protocol. And because this semi-definite program is computationally efficient, they can go back if they're not happy with the protocol and tweak it a bit and then recalculate the resulting rates. And they can do this many times and just optimize the protocol to fit the devices that they have. And this is very important because in device independence, if we really are independent of the devices, we can't really assume that we're able to tune the devices to better fit the protocols that we have. But we can tune the protocols now to fit the devices. Okay, how much time do I have? 10 minutes. Oh, yeah. Okay, this is going a lot faster than it was before. Okay, so yeah, so what we did is now we have this, we showed that we can create these protocols in general. So we took our framework and we computed a few example protocols. And what we wanted to look at is how robust these protocols can be to some particularly relevant noise models. So if we look at, we looked at our devices and we pretend that they're sharing some qubit system, so some partially entangled qubit states here. And we're going to look in the situation where we have 2 inputs on Alice's side and 3 inputs on Bob's side. And for each input, we have binary outputs. And we're going to look at how the randomness accumulation rates are affected by inefficient detectors. So by an inefficient detector, we mean that when the state comes to the measurement device, with probability eta, it's going to be successfully measured, and we get the correct outcome. And with probability 1 minus eta, it just outputs 0. And so we built a few different protocols around some different non-locality tests. And now this first protocol here is kind of the benchmark for what is good. So this is the protocol that Glaucia spoke about earlier, where we have this analytical bound on the von Neumann entropy for one side. So we play the CHSH game and we get a direct bound on the von Neumann entropy. And now we look at a slight extension of this, where we have the CHSH game now, but for x and y equal to 0 and 2, we check that these 2 inputs are perfectly correlated with each other, or we check how correlated they are with each other. And then it should be, if we have a maximum violation of CHSH and perfect correlations, that these 2 inputs here should be perfectly anti-correlated, or perfectly random. So in this way, we can generate up to 2 bits of randomness per entangled qubit. And also, we looked at a third protocol where we try and get the most amount of information out of our devices in a device-independent way. So that would be to look at the entire distribution with which the devices are acting. So we don't coarse grain the information into a CHSH inequality. Instead, we actually look to try and estimate the entire empirical behavior. And so the results of this plot, we had a look. This is the benchmark protocol. So it generates up to a bit of randomness in the IID setting. So this is as the number of rounds tends to infinity. So the dashed line is really the best you can possibly do with this technique. And this filled line here is the entropy accumulation theorem rate that we can certify using our techniques. Well, this is for the benchmark protocol, and we chose protocol parameters that were reminiscent of the recent photonic loophole-free bell tests. So this is actually plotted for parameters that are realistic currently. And so if we look at our min entropy now, what we find is that, yes, we can generate 2 bits of randomness in the noiseless case, but because of this relation between the min entropy and the von Neumann entropy being not tight, we actually drop off very quickly. So once we get to about 0.96 detection efficiency, it's actually better to use this benchmark protocol. And even when we look at the full empirical distribution, so we track as much information as we can, we get a much more robust curve in the asymptotic regime, but the finite bound we get is, because we're tracking so many scores, it suffers a lot from the effects of finite statistics. And so, kind of the conclusion, we've shown that you can use these numerical techniques to generate secure protocols, and you can fine-tune these protocols to fit the devices that you have to hand. But the real big problem here is the fact that this inequality is generally not tight at all. And what we would really like to do is get a bound on this quantity here, but yeah, in general, we can't do it. So possible ways out of this, we could look at trying to get numerical hold of some different entropic measures. So we looked at the min entropy here, but there's an entire family of entropies. The Renyi entropies, we could look at different ones in that family. There are many different families, and as long as they obey this inequality relation, we can, if we can get a handle of them, we can use them to try and generate security of our protocols. Instead, we could also look at larger scale semi-definite programs to make more complex protocols. But this is at the cost of experimentally it becoming more difficult. So actually we can increase this this noise robustness all the way to 0, but this is going to create an incredibly complex protocol. So if we look at multipartite protocols, there's a certain family of GHZ protocols which in the limit of the number of parties, you actually get a detection efficiency of 0 is required. But yeah, you're going to have to generate n-party entangled states, and nobody wants to do that. As well, another thing we could have a look at is the semi-device independence. So we can add additional assumptions into our protocols now to try and gain some extra analytical power. But again, finding a good assumption to add in here that we can easily check is a difficult question in itself. So, and with that, I thank you for your time.
Questions?
Okay, my question is about like the general protocol, because you need some randomness on the inputs to start with, and you are doing randomness expansion, so I don't clearly see that one.
Yeah, I kind of glossed over that bit. So, yes, so in this device interaction phase, we're going to split the rounds into testing and generation rounds. So in order to characterize these devices with non-local correlations, we only need a certain number of tests until with high probability these devices are well characterized. So actually we only test with a very small probability. So we only need a very small amount of randomness to do this in total. So with probability eta, we're going to test the device where eta is going to be very small. And then most of the time, we're just going to give the devices fixed inputs. But the idea is the devices don't know when we're going to test them. And so in that sense, yeah, that's where the expansion comes from. But yeah, I kind of glossed over that bit.
More questions?
Hello, thanks for your very nice talk. I would like to ask you about your results plot, because there was a thing that surprised me a little bit. So I wanted to ask you to actually comment on this. If you take a look at your blue line and your orange line,
yeah.
You said that the blue line actually takes into account the full statistics, right? You don't. But why does it perform worse than the CHSH plus the correlations? This is sort of
it's
like
because
not intuitive, really.
Yeah, so the problem is finite statistics. So we're tracking, so in this protocol here, we track the CHSH inequality and we track the alignment score. Now here we have many different probabilities to track, and so if you think about the finite statistics, we have errors in every single probability. And so these errors kind of add up and accumulate, and so if we don't have enough rounds, we can't be certain about the probabilities themselves. And so the more scores you have, the more rounds you need until this curve pushes up to the dashed one. So we could actually make this curve go higher, but we'd need more rounds, and we decided to keep the parameters at a realistic.
Okay. Maybe a follow-up question. Have you considered using multiple Bell inequalities that you evaluate from the same statistics?
Yeah, so this is I mean, you can think of
Sort
the
of, okay, I
empirical
see.
behavior as multiple.
But have you
Bell
tried to
inequalities.
optimize over this, maybe like trying to find different sets of Bell inequalities that
Yeah,
do
so
well?
that's something we're looking into, but this is, you can think about this as being the best you could do, really. If you're looking at the full distribution, you can't find another set of Bell inequalities that's telling you as much information as this. But I agree there could be a
But you might
smaller
get rid
amount.
of the statistics problem because
yeah,
there's
yeah,
like less parameters.
Exactly, yeah. So we've looked into this, but it seems that, yeah, you can't really find a good amount. So we have some other protocols in the paper, and they drop off at a similar rate. Basically.
Okay, thank you.
More questions?